Okay, good morning, everyone. Hopefully you got some rest. See, you're all chippy. Back from the spring break. Good. Well, we'll have one more week of circuits, which is this lecture and the next. And then we're going to transition into the locationing module, where you'll learn more signal process, or like intro to signal processing, like correlation, least squares, and some of these techniques that are kind of more advanced linear algebra things. They're fun. Thursday lecture, we're going to do a little bit of a review of circuits. So I'm going to put up like a Piazza post to ask people for input. Like, if there are things that you feel shaky about, like just type it in and I'll try to cover some of these topics, okay? So that will be the Thursday lecture. Today, we're going to focus more on some interesting designs with the toolbox that we kind of acquire, right, so far. So let's say the first design, you get asked to build, okay. Voltage-controlled current source. Right. So what is the first step in the design process? So I tell you, go build a voltage-controlled current source. The first step you're going to say is what? Yes?
Specify what the circuit needs to do.
Yeah, so you're going to say, wait a minute, what do you actually want? What do you want exactly, right? And then I'll have to say, well, I want a current source that is controlled by a voltage without disturbing where that voltage comes from, right? So I'll have to go and draw something like this. I have to draw something like this and say, okay, I want you to draw a circuit that will behave like this, right? Between these 2 points, let's call them A and B, it will measure the voltage VC. And based on that voltage, it will determine the amount of current that is in this controlled source to push out of these terminals, C and D, regardless of what load is attached here, right? So there will be some load here, right, that I can later attach to this source and use it. It could be a resistive load, could be capacitive load, a mix of the two, some more complex circuit, whatever, right? This circuit will always try to push GVC amount of current through this, where VC is this controlled voltage. Does that make sense? You're designers. So I gave you a little bit more detail about the specification. Okay, good. So, step 2. So step 1, we're going to say state objective, state goal, or specification. What is step 2? Now that I know what I need to build, what do I do in step 2? Yes.
You need a strategy with the components.
Okay. So we need a strategy. Game plan, right? That usually involves the understanding of not exactly a toolbox we're going to use in the next, but physical mechanisms that you can use, right? In touch, in resistive touch, we said, oh, Ohm's law, okay. And based on Ohm's law, we figured out everything that, how do we sense the voltage, the resistive divider, etc. In capacitive touch, we figured out basically CV, Q equals CV. That was our fundamental equation, and from it we understood that we can do measure variable capacitor, turn it into variable charge on a fixed voltage, and then later take that fixed voltage on a known capacitor, or fixed change in charge on a known capacitor, turn it into a change in voltage, right? So that was the game plan, just based on that Q equals CV type equation, right? So here we want, again, to have a physical insight that will allow us to somehow turn voltage into current, right? So maybe, you usually draw like a diagram of some sort that will tell you what the progression is. So maybe the progression is, what, like panic, and like come back, right? So that's one strategy. Another one is to think about what physical mechanisms you actually learned in 16A, right? So we learned Ohm's law, we learned the link between charge and voltage on a capacitor, and pretty much these kinds of things you could use to create some sort of a sensor, right? So okay, we're not gonna do this, right? So the 16A approach is to say, well, it's a current source, voltage controlled. So what is the easiest way for me to control a current with some voltage supply? Yes, a resistor, right? So if I have a resistor, R, and I add some voltage to it, right? Then this current is how much? IR is how much? Vs over R, right? Okay. So I'm so close, right, to here. The problem with this is if I say that this 1 over R is my G here, the moment I add something to this, the situation will change, right? First of all, I don't have, in this situation, let's see how do we model VC, right? VC, there's some circuit. Circuit is, let's call it circuit X, right? Circuit X has a whole bunch of supplies, current sources, voltage sources, resistors inside, and then there are these two terminals, right? A and B. You can view them not as terminals, just some nodes in that circuit, right? There are nodes A and B. And VC is the control voltage right there, right? So how can I model this circuit for the purpose of my design? Right. I know that inside there are some, voltages. I don't know why this is. Some voltages, some current sources, some resistors, right? So, and I have these two terminals, and I want to know the equivalent model of that. What is that? Yes? Thevenin, right? So I can replace all of this with Thevenin source and a resistor. What is the value of the Thevenin source? If I tell you there's a whole bunch of junk in here and VC is the voltage between terminals A and B, and I want this thing to exactly give me that, right? Voltage VC between terminals A and B. What is VThevenin? VC. Right. Okay. So I want now something that where this voltage will stay VC regardless of what I add to this circuit. Right? If I added this, right? So if I replace this with R Thevenin, and this is point A and B. What is now the current? It's no longer Vs over R, right? Yes. Well, it's this VThevenin, right, over R plus R Thevenin. Right. So the problem here is that the moment I add, so this is the resistor that should be defining my G, right, over here. But the moment I add that to the source, I have a problem here because the current's actually flowing, right? Here. And think about our specification here. We wanted to do a measurement with an open circuit, right? So what we did here, by establishing this current, this voltage here is no longer equal to VC. It's some divided version of VC. So I haven't really done the right thing. My objective was to have this current be driven by this VC voltage, which is actually VThevenin. Does it make sense? I wanted to create something that, the source here is G times VC, where this G equals 1 over R. That's what I want to do. Right? But here, that's not the case, because the moment I hook this up, there's this R Thevenin term that creeps in. And I don't know what that is. That's some junk in that circuit. Right? So it kind of messes up the value of G. Okay. So this is basically called loading effect, right? Where whatever circuit we add to this circuit X, we're kind of loading it. Right? So we're going to change what that control voltage is. So what kind of circuit can we add to circuit X and not load it? Yeah, we could do a unit gain buffer, right? So we have our circuit X, terminals A and B. This is control voltage VC. So just going to add a unit gain buffer. Right, I can ground this. So this is voltage VC. So then the output here will be how much? What is the output voltage going to be? VC, right? But there is a major difference here. If I now attach any load here, what is the voltage going to be? Still VC. If I attached any load here, just like simple resistor, the voltage would not be VC anymore. Right? And that's really important. In other words, if you want to see it kind of as a model, this is our V Thevenin equals VC. R Thevenin goes into a buffer. Right? First golden rule, this current is 0. So the voltage drop across the resistor is 0, and VC is the voltage here. Right. Does that make sense for everyone? Okay. So now we got ourselves a good control voltage. It can take anything, right? Now we need to make current out of it. Okay? So what do we do? Yes? Okay, you're getting somewhere. Let's first figure out how do we turn voltage into current, right? Okay, so you're saying, okay, let's use a resistor. We're gonna add the resistor R here, right? This was VC. So what is the current through this resistor? Yeah, so this IR will be equal to VC over R, or G times VC. Right? Am I done? Okay, yeah, this is a great point. So at this point, you may say, oh, I'm done, a happy farmer. I've generated current, I'm done, right? The problem is, this is a useless circuit. What I really wanted in the specification is not only to produce the current that is G times VC, but I wanted that current to drive a load, an unknown load. Right? And in this case, this current is produced by control voltage over R, so I need to know the exact value of the load to produce the current, right? If I add any other load here, so that says this is R load, right? If this is some R equivalent R load, how does that change the current? I just added another resistor in series, right? So now VC is actually, VC is always to ground, right, from the output. So how does this current change then? Is it still VC over R? What is it? Yeah, so it's now, instead of this, it's actually VC over R plus R load. And you're right, I'm kind of getting the same situation as up there, right? Over there, I had the uncertainty from my source, right? Because I had this R Thevenin that was messing things up. Now I have an uncertainty on my load because I don't know what this load is. I don't want it to affect the current, but it's affecting it, right? So how do we fix that? Yes? Okay, how would you do that? Some sort of feedback involves some circuit, right?
Yeah.
What element?
I'm not sure.
What do we, like, what circuit block is kind of the heart of every feedback system, negative feedback system? Op amp, right? So we need another op amp, right? So we need an op amp that would isolate, somehow put like some sort of a known potential here so that we can define the current. But the op amp needs to put the known potential here, preferably 0, right? Without stealing current, right? If I put a 0 here, then I have a defined current, VC over R. And then as long as that current can be shoved into RL instead of the op amp, I'm good. Okay? So let's take a look at that. If I have some VC here. You sort of know that circuit already. And I have an op-amp here, right? And I have an R. So this is my R. And let's say I have some load RL here. How should I connect all these elements to make sure that the current that flows through R is VC over R? Right, that's the current I want. And then that current also flows through RL. You've seen this circuit before. It's an inverting amplifier, right? Right? So what happens here, VC, that's the voltage that this buffer is generating, right? So we can even draw that buffer, right? This is the buffer, it generates voltage VC. This is an inverting amplifier. What is the voltage at this node? Yeah, second golden rule, right? The op-amp is in negative feedback, therefore V plus equals V minus. So the voltage here is 0. The fact that this voltage is 0 is really sweet, because now the current here is only determined by VC minus this 0. Right? So whatever is happening on the load does not influence it at all. Okay? And so we get just clean VC over R. Then, as that current goes this way, it hits this node. What is the current going into the op-amp? 0. That's the first golden rule. Right? And so that makes all this current VC over R flow this way. And instead of VC over R, we can write GVC. Right. So I've achieved exactly what I wanted. GVC is pushed into the load, whatever that load is. Right. Okay. So that's essentially our voltage-controlled current source. So, step 3 that we kind of skipped to define, but I'm just going to recap it here. Step 3, what we did in that step was we did implementation, right? Now, as some suggestions came from you guys, you were using what we call a toolkit, right? Implementation comes when you have some, Lego blocks with which to build. And the Lego blocks is, for now, is your 16A toolkit. Right? So what do you have in that toolkit? You have resistors. Caps. What else? What did you learn in terms of circuit components? What's the coolest one? Op-amps, right? And then we have sources like supplies and current sources. Right? If you take a look at this list, it's actually not that big. It's not that long, right? It's like 5 components. That's pretty much all you need to build these circuits, right? So just keep that in mind. So it's one part of the toolkit is these, let's call them bare bones components, right? So this is components. Another part of the toolkit, actually there are 2 more parts that I recommend. So different people have different views. So these components. Second one are blocks. blocks are things like resistive divider, current divider, or so let's say, sorry, voltage divider. Voltage divider, I'm going to put both R and C because we can realize voltage dividers with capacitors too, right? Current dividers. In this category of voltage dividers, we also have level shifters. As you'll see in the discussions. Right. These are usually R, but can be sometimes a C. Right. Then we have, these are pretty much all of the things with R's and C's. And then we have this whole bunch of blocks that we've done based on op amps. Right. So you have a buffer. Then we have non-inverting op amp. Inverting. Then we have trans-resistance. Actually, one more thing here to add is a summer. And then we have inverting and non-inverting summers. Right. All these blocks we've done in the lectures so far. And in discussions, kind of, you've seen, yes? No, trans-resistance amp. Right? Trans-resistance was basically, let me remind you real quick, it kind of comes from this. It's just instead of VC over R, using R in this branch, I use a current source. Right? So I can draw it like, basically like this. Right? So current comes in, comes directly through this R, generates voltage on this R because this is ground. Then the output is just, if this current is I, this is R, the output is minus I times R. Yes? This one over here? The one above? This is inverting, right? There's a resistor here and there is a resistor here, right? So from the standpoint of the output voltage, will be equal to minus RL over R times VC, right? But in this case, we didn't care about that voltage necessarily. We just wanted to generate a known current through this branch, right? Yes?
So if we said that the current source on the bottom has value VC over R, we can take that circuit.
Correct, but you need now a current source, right? Yeah. What was about to, yes, okay. So that was the trans resistance. Now this current can also come from some other thing. For example, last lecture we did an example where this current was actually photocurrent from the photodetector or solar cell, like you have in your homework, right? Or you did in the lab, basically the same thing, right? Where you receive some light and then you need to detect that photocurrent and turn it into voltage, then your Arduino board can detect, right? So that's that piece. So for all of these, it's very useful that you know kind of what we call a transfer function, the relationship between input and output voltage, or input quantity, if it's current, and the output quantity. So that you can quickly compose different blocks. Right? So try to practice these kinds of things because when you're thinking about the strategy, you want to know the physical principles. When you're thinking about implementation, you want to have these blocks ready in your mind just like Lego blocks. How could you quickly put something together? You still don't need to use them, but you could say, oh, this looks like a sum. Okay, I'm going to use some sort of a summer. The next thing, oh, I need an opposite sign, so I'm going to use some sort of an inversion. You don't need to know yet exactly the components and values, but you just need to know the function of the block. And then later you're going to see whether you need any isolation between these blocks to prevent things like this, right? For example, here we use the buffer, right? Because some of these blocks need isolation, some don't. Right? Yes? A summer, well, okay, let's do that. We might as well recap a little bit along the way. So, the simplest summer was this. Right? So, can someone tell me what V out is? Or maybe talk to your friend for like 30 seconds. And let's see if you can calculate. Okay, anyone? Yes?
R1 times the V1 plus R2 times R1.
Okay, I'm going to write it, and then we're going to see if everyone agrees, okay? Okay, do you all agree this is the solution? You're saying this is a minus? Okay, what technique are you using to do this? Superposition, okay. Yeah, that's correct. Okay, it should be like this. And why is it like this? Well, if we are calculating V out as function of V1, we null this source. Right, so then it's a voltage divider. It's whatever voltage is dropped on R2, because this is now grounded, right? Meaning the equivalent circuit is V1, R1, R2, and then we're measuring this, V out 1, right? So then it's R2 over R1 plus R2 times V1. So it's R2 over R1 plus R2 times V1. And then the second component is the opposite. I null this, so I have R1 V2 over the sum of the two resistors. Okay. Still, this is a weighted sum of the two voltages. It's weighted by the first coefficient. I can write it as alpha 1 V1 plus alpha 2 V2, where alpha 1 and alpha 2 are smaller than 1, right? Because they're the ratios of each individual resistor over the sum. Right? So you can use this, right, in a lot of your things. You just need to know that, okay, whenever you use this, the coefficients will be less than 1. So then if in your problem you're asked for coefficients that are greater than 1, you need some sort of an amplification, right? Either before, if it's one of the coefficients is greater than the other, or after, that you can gain everything up. So there are some small things to think about. There's another summer that you can use. So this one is just pure summer. If you need to amplify, of course, you could take, okay, well, let's do this. Okay, if you want to amplify that V out, obviously you can put it into some sort of a non-inverting amplifier, right? Right, this will be my So this voltage here to ground will be my V sum, right? And that I would amplify that V sum by 1 plus RA over RB, right? And here I will be getting V out 1 plus RA over RB times V sum. So I don't even need to solve these things. It's just block composition, right? And I can do this because current here is 0. Right? So these non-inverting guys, they're composable. I can just add them to the previous block. They just measure the voltage. It's all good, right? So there's another type of summer that we can build, and it's kind of based on I guess we erased it. So I'm gonna on these non-inverting amplifiers, right? So you can do, I think we did that block too a few lectures ago, but here it is again. V1, R1. Right? This one. Here, we do it by summing the currents, right? So this node is 0. So this current is V1 over R1. This current is V1 over R2. None of that goes into the op-amp, and both go through R3. Right? So you'll immediately see that you're basically, so the output will be minus R3 over R1 V1 minus or plus R3 over R2 V2. So that's the output voltage. You can also do this by superposition, like we did a few lectures ago. But this is an inverting sum. Notice that this one is nice because I can immediately set these values to be whatever. Smaller than 1, larger than 1, etc. Just by the ratio of R3 and R1, and I can set them independently. Right? In this one over here, I always have this, if I change R2, these two are also connected through R1 and R2. So it's a little bit harder to choose independent scaling coefficients. Right? In this one, it's very easy. You just change R1 or R2 independently. Yes? A level shifter, that's a great question. So in this situation over here, as a summer, imagine that this is my signal, right? So we draw it as something like this, right? But I want this voltage, that signal, to move from, for example, here it's changing between, let's say, 1 and 2 volts, right? And I want it to change between 0 and 1 volt, right? So then I will add a supply here, right? And when you go through the math of this sum, you will see that now this will be changing in some, if I, for example, add here -1, right? This supply is -1 volt, it will pull this voltage down by that much. Yeah, you don't need it. Yeah. But then to use that signal, you will need at least a buffer, right? Because the moment you don't want to add any load to this circuit, it will disturb this voltage divider. Right? In fact, I think you're going to learn about level shifters today in discussion, actually, when we talk about like level noise canceling headphones. Yeah. Okay. So components, blocks, and then the third one is basically how to compose things. Right? So third one is composition. So this is loading. Right, you need to watch out whether the circuit that you're putting, you know, what we did is like, okay, a summer, and now I'm kind of inverting it with some gain A, etc. Right? So it's my signal processing chart, like we did in discussions. Each one of these blocks is some block from this toolkit, but I need to know, can I compose them like this, or I need to insert a buffer in between to maintain their function. Right? So that's the key. Okay, does it make sense? If you follow this recipe, it will be easier. You know, it's always kind of, the first step is the trickiest, which is figuring out this based on what physical mechanism you're going to structure your strategy. Once you have that, the rest will flow from the toolkit and the blocks and will be, I'm not saying easy, but like easier. Right? But the first step to see, okay, what mechanism do I leverage, that is kind of trickiest. Luckily, you only have like two. Right? It's either something to do with voltage and current on a resistor or something to do with capacitor. Right? And so you can see roughly, based on what's being asked, which of these two, and then try to go that way. Right? So let's see how much time do we have. Okay, we can at least start the next one. This one is a lot of fun, so hopefully you'll like it. So step one is, I tell you, I want you to build a timer. Right. So let's build a timer. And you say what? Let's be more specific. Is that like what is it? Is that some sort of like a clock that needs to wake up every once in a while? What are you talking about, right? So, okay, then I'll go and say, okay, well, I want you to create actually a voltage that will look like this in time. Right? So there will be, let's say, 1.5 volts here, minus 1.5 volts here. This we're going to call a period T. This here will be half period. Right. So half of the period, the voltage is high. 1.5 volts, half it is minus 1.5 volts. Okay? And this T period is set by components values. Right. So that's a very detailed specification. Right. And I want this V out to be able to drive just about any circuit. I want to use it for a lot of purposes. This is a timer because it gives me a sense of time. I will get this rising edge every t seconds, right? And that, based on that, I can do stuff, right? This, in digital systems, this is called a clock. And so all your processors, everything you have in your pockets that does digital processing has one of these inside. And information flows and is computed basically on this clock cycle. So every clock cycle, which is basically this period, new information gets into your digital circuit and new information comes out, right? That's one example. There's many other control systems, whatever, where you need this sense of time. Even when we did the D to A converter example, there was something that had to switch the switches, right? Well, this can switch the switches, right? Phase 1, phase 2. In our capacitive sharing thing, phase 1, phase 2. I can use this to basically do the charge sharing, right? So many uses for this type of timing source. So okay, let's see how to build it. Step 2. Strategy. Okay. Let me give you like 30 seconds, 1 minute to talk to your friends, see if you can come up with some sort of strategy. Do we have what? We haven't learned about AC sources so far. We just know what signal is some changing supply source or changing voltage source. But AC by like alternate current, no. Okay, here, don't worry about implementation just yet, right? We're just talking about the strategy. What physical mechanism or what property of things we'll learn you can use to try to generate time, right? Yes?
First you need some like time varying thing, source, and then something to like set it. If it's positive, then 1.5, if it's negative, then negative.
Okay, I mean, you're going along the right track, but like, it's not a physical mechanism, right? That's just like, that's more like implementation. How are you gonna do it? Like what physical thing that relates the components or some properties? You had a comment? Sure, that's kind of what we're gonna use in the end to generate the flat, right? But even just like notion of time, right? If we use resistors, do we have time? Notion of time? No. So, yes. Okay, you're really advanced. Okay, just because of you, I'm going to show you a circuit like that in the end, but it's, yeah. We want to use something that you know how to analyze and implement, right? That RC exponential kind of thing is kind of tricky thing. We said it's out of the scope, right? Yeah, yes. Okay, capacitors and switches. So in a nutshell, let's say just a capacitor, right? If I have a capacitor, oops, I wanted to draw a capacitor. So I have a capacitor C. It has current coming into it, IC, and voltage VC. Right? IC in this scenario is defined as C times delta VC over delta T. So you see this delta T here? That gives you kind of a hint, an inkling that this element has something to do with time. Right? So I can kind of use it to try to figure out, get some notion of time. Right? Resistor, Ohm's law has nothing like this, right? So there's no way to get some time information out of it. But out of capacitors, you can. So let's say I take this element and I add a current source. IS. Right? What is going to happen with voltage VC? So if I draw VC as a function of time, how is this VC going to look like? Okay, you're saying linear. Linear, how? Increasing, decreasing? You don't know. Slope is C. Okay, well, let's see. Let's take a look at this equation, right? The slope of voltage is dVC dt. Right? This is slope of VC. So what is that equal to? So it's IC over C. So in this case, what is IC? It's IS, right? So in this case, IC equals IS. And therefore, the slope is going to equal to IS over C. Now, I haven't told you what the value of IS is. Let's say IS is positive. Okay? So how is this waveform going to look like? Yeah, I'm seeing some, yeah, like this, right? Okay, this is a great question. So here we have a dilemma. This is only a small capacitor, right? With some value, C. Maybe not small, maybe it's big, right? But it's a finite capacitance. And here we are dumping all this charge on it all the time. Like what happens? Does it explode or what happens? In ideal world, anything can happen, right? So let's just see first what's the trend, right? And then we'll see whether something prevents that trend from going on forever, right? So if you just look at this circuit, what does it tell you? What does the basic physics tell you here? How does the VC change? The gradient is constant and positive. So what is the VC as a function? It's a line, right? It's a line, and it increases. So this gradient is IS over C. Now, you're right. This basically indicates that the voltage on a capacitor increases to infinity with time. And indeed, if you think about it, as I'm dumping charge on this capacitor, it's harder and harder to add new charge. It's so crowded over there. It's like San Francisco. It's like adding another, apartment. It's kind of hard. And so basically, it's harder and harder. And the price for adding a new piece of charge is basically higher and higher. That's your voltage, right? But this guy has like an infinite supply. Like it's like Google and Facebook employees buying housing in San Francisco, right? They have an infinite supply of money, and that can dump on there, and you're good. As long as the stock is increasing, you're fine, right? So in an ideal world, right? Of course, something happens, right? In real world. What happens in real world?
Discharge. Discharges through the air.
Through where?
Across the plates when I'm leaking.
Yeah, so as the voltage increases and this distance is fixed to L, there's an electric field in here, right, that grows with increased voltage. And essentially, at some point, you will hit the so-called critical field where air is going to discharge. Right? So now air is going to break down. It's called a breakdown voltage or breakdown field. And you're going to get a little lightning from one plate to another. And now, essentially, the charge will unite kind of on the plate. So you're going to get a decrease in charge on the plate, and your voltage is going to drop. Right? So that's kind of a limit up to which. So there is some physical limit. We're going to call it here like V critical. Right? But that's, for capacitors, that's like it's a pretty big voltage, right? Depending on kind of the gap that you have in the capacitor. We don't want to operate our timer there, right? This is just saying, okay, I just want to use this slope. So in order to prevent me hitting that limit, what would I need to do with this current? Detour it. I could do that, but what I really want to do is I sort of want to repeat a cycle. Right? I want to rise for some time, and then I actually want to go down for some time, so that I can rise up again. Right? And that kind of starts reminding me of this. Right? Here I'm high a little bit, but then I'm low, and then again, etc. Right? So here I'm not rising the same sharp slope, but we'll see later how to fix that. But so I would want, this gives me something that we call like a time base, right? It's just relating voltage and time. And now I want to switch it so that I can go down. How do I do that? So if I switch it to ground, I will just do abruptly something like this, right? So yeah, you're right, you can do that. That's okay. But I'd like to sort of maybe do more gradual thing. Charge sharing. That will just instantly kind of, again, create some change. I want to gradually kind of ramp it down. Just the same way it came back up. Yes? Yeah, so I need to switch the polarity of this current source. Right. So I can do it by, for example, adding a few switches. Oops. So here I had one source. So here it is, right? Switch 1, switch 2, they work in the opposite phases. So first S1 is on, we get a circuit that's on top. And if we're drawing VC, VC is a function of time. It increases. Here S1 is on, S2 is off. Then once it hits some level, let's call that level V1, we switch. So here, in this other period, S2 is on, S1 is off. Right? And then we have a circuit that looks like this. Right, so now I'm taking charge out of the capacitor. Right? So here the slope is IS over C. Here the slope will be what? Negative IS over C. Right. And so let's say I started from some voltage V0. I'm going to get to that same voltage in the same amount of time. So this is going to be delta T. This is going to be delta T. So let's calculate that delta T. Right? It's all from that equation above. I have dVc dt equals, in the first phase, IS over C, right? Because this is constant, I can write this as just a difference, right? So I can go and say it's V1 minus V0. So that's V1 is my last point, V0 is my starting point, over time. Delta T equals IS over C. Does this make sense? Right. I mean, I could have written an integral and everything, but because it's constant, it doesn't matter, right? I just wrote it like this. So from here, delta T will be C times V1 minus V0 over IS. And this is actually a cute expression, because it kind of tells me what's going on. C times this change in voltage is what? What is this quantity over here? Change in charge, right? This is how much charge got dumped onto that capacitor, right, during that rise. And it got dumped at a steady rate of IS. And we know that current is basically change in charge over change in time, right? So that all makes sense. Okay, and then for the other slope, I could write the same thing. It would just be, okay, the change is now V0 minus V1 over delta T equals minus IS over C. Right, so you see it's the same, it will lead to the same expression. Right? We could call this delta T1, delta T2, but they are the same. Yeah, CV1 minus V0 over IS. Okay, and then again, we'll go up and down. So by being able to get these switches on and off, we create this ramp. Now, you may say, well, gee, if I could turn these switches on in the first place, like why do I need, I must have had a timer in the first place to do it, right? So there's like a chicken and egg kind of thing here, right? And you're right. We're going to show you how this is all going to come together, right? Now let's first figure out how to use that, how to turn this ramp into that pulse stream. Right? So we have a circuit here which has this ramp. How do we turn this like triangular waveform, periodic, into a rectangular waveform? Do what? Take a derivative. Remember, sure, you could do that, but for that you need some sort of a circuit, right? How would you do a derivative? You could do it with R and C, but I don't want to burn you with that. So, yeah. Okay, and? Okay, so you're saying like an op-amp as a comparator. Yes, okay. So, say we take that circuit. IS. And we here put the supply of 1.5 volts and another supply of minus 1.5 volts, right? And this is our V out. Okay, so now let's figure out how to work the references here. The nice thing about this op amp is it does not load this C, right? So whatever is VC, which is the voltage here, will come into this port. It will be just measured, just like you did in the touch lab, right? So now what else do we need on that comparator to be able to generate the pulse train? Yeah. Yeah, so where would we put that reference voltage? We put it where? At 0. So this is like V1 and V0. I don't know what these two values necessarily are, right? So if I put it at 0, I'm never going to cross. So remember, that's the output, right? The output will be toggling depending on the V plus minus V minus. Yes? Yeah, so one strategy could be, okay, I place it here, right? So in that case, I could have my Vref equals V1 plus V0 over 2. Something like this, right? And then, indeed, whenever I am above, right, the Vref, I will just generate 1.5 volts. When I'm below, I'm going to generate minus 1.5 volts. Okay. Problem is that, I'd like to somehow get rid of these switches in the end, right? And so if I do it like this, I have no way of doing that. Right. So the way I can also do it is, instead of doing it like this, I'll do something unorthodox first. Okay. Okay. So I'm going to do something like this. But in this case, I do need to make sure that my V0 and V1 are indeed aligned with 1.5 volts. Okay. So let's first take a look at what I did here. Okay. Is this circuit in negative feedback? No. This circuit is actually in what we call positive feedback. Right. So it's crazier than ever. Okay. So when this input is very, very low, right? Then this output is going to be what? Regardless of that input. Now, let's say that input is minus 2 volts. This output will be 1.5, right? Because minus 2 volts here, whether this is minus 1.5 or I can assume that this could be minus 1.5 or 1.5. If it's minus 1.5, still there's positive voltage developed here, so that should slam me into 1.5. Right? So you always, in these kinds of circuits, you always know it's going to be in one of the two states. It's either going to be high or low. And then you test the input for each one of these and see what's true. Right? So if this is minus 2 volts, well, whatever I assume here, whether it's minus 1.5 or 1.5, it's going to give me 1.5 here. Right? So in that case, I know that the output is actually 1.5. This has to be 1.5. Right? So then this starts increasing from this very small voltage. So it's increasing up. What voltage does this need to hit for the op amp to react? So VC starts increasing from some very small voltage, right? Let's say minus 2 volts. What voltage does it need to hit so that this circuit changes its state? Yes. Yeah, so let's say we start VC from minus 2 volts, right? And then I look at this terminal and I say, okay, what can V plus be? V plus can be either plus 1.5 or minus 1.5, because this is a comparator, right? So if it is minus 1.5, then V plus minus V minus will be minus 1.5 minus 2, right? That's still 0.5. That's a huge voltage, right? So with this much voltage on V plus minus V minus, the output is for sure 1.5. And if it's positive, you get even bigger, right? So it's definitely saturated at 1.5, right? And so now you know that this terminal is at 1.5. So as VC increases, at what point does this thing trip? Yes?
When V minus is greater than 1.5 volts.
It will be what?
When V minus is greater than 1.5 volts.
Correct. So VC or V minus, right? VC equals V minus. So when VC V minus is 1.5 volts, so 1.5 volts is equal to V plus, right? That's here. So when VC increasingly gets there, and just a little bit above, right, this thing will flip. So the output will now go from 1.5 to minus 1.5. Okay? So what happens in that case? Just as we went a little bit above, the output flipped, and this is now minus 1.5. But this is still a little bit above 1.5. Right? So now, you flipped, V minus is bigger than V plus, it's going to stay there, right? So now, if I use this opportunity, this flip, to change my sign, I can now start going down. So what I'm trying to say is that this you can use to drive these switches. Right? If a high voltage on the output drives S1 on, that means you're integrating up until you hit the threshold. When you hit the threshold, you will change the polarity. That change in polarity will turn off this switch, turn on this switch. Right? And then, so S1 will be on here, S2 will be on here. And that will make this going to start coming down. Now, as it starts coming down from 1.5, and this is minus 1.5. That's where the next change happens. So this is minus 1.5. When V minus gets a little bit below minus 1.5, what happens? Yes? A flip, right? Because V plus, this is now V plus, right? So the moment V minus gets below, comparator senses a positive voltage, and it will rail this one again to 1.5. Okay, so let's maybe draw a time diagram of this so that you're clear. So this is VC, and this is V out. So let's say at some point at the beginning of time, doesn't really matter, we started from some value. That value is, let's say, minus 2. Right? And we started ramping up. During that time, as it is minus 2, the output was basically high, was at 1.5 volts. all the way up until VC is at 1.5 volts. When VC hits 1.5 volts, the comparator flips. Right? The comparator flips and generates minus 1.5. Now, I will say that S1 is on when V out is 1.5. So this is S1 on. And S2 is on when the comparator flips the state. So if S2 turns on when the comparator flips, I'm going to start discharging. Okay? And the moment I hit minus 1.5 in discharging, I'm going to compare to this level. Right? Because this level of V out goes back to V plus. So I'm comparing to V plus equals minus 1.5 volts. And then the comparator snaps back. When the comparator snaps back, I'm going to say S1 turns on again. And I start rising again until I hit, again, 1.5. And then the story repeats. So now I still haven't shown you how the comparator actually turns the switches on and off. We're going to do that in the next lecture. But we're getting there. Very close to independence. Okay? Thanks.